So, I got it.
That's positive. Right. But it's just positive.
So questions about homework? Yes, sir. Go ahead. Go ahead. All right. Can you give me specifics on it?
It's finding the J at like a position in the H field.
Give me the H field.
H equals Z over sine B.
Z over
Sine B, yes.
sine what?
B.
B, okay.
And then A rho direction. Rho minus rho squared over cosine B. And the AZ direction. And it wants it at a point which is
They want J, right?
yeah, J at a point, which is 3 meters, 60 degrees.
So it's rho equal 3, right? B equals 60, right?
Yes.
What else?
And then 4 meters from Z.
Z equal 4. Okay. So the whole idea of doing this is just to get you at least somewhat familiar with doing the curl. Remember that curl of H is equal to J. That's all it is. Now if you look in the back, I would give you the curl for this one. If you look at the back cover of your book, and the curl is the third operator that they show. This is cylindrical coordinates, and my book has it wrong. They have it in Cartesian coordinates. Does your book have the right curl or not? I mean, but look at the definition. Cylindrical is it ddx, ddy, ddz. You have rho, you have that in yours, class?
Rho B.
Mine has the wrong. Does anybody have the wrong? This is an older book. Y'all have it right?
Mine didn't match the answer.
I'm sorry?
So mine didn't match what's in the answer.
Okay, well, we can do it, but here's the bottom line. We have to take a curl of this operation, and then we have to evaluate it to this point. That's it for J. Y'all follow me? So what's the definition of curl of cylindrical coordinates? If you aim the cylindrical coordinates, what is it? I mean, I don't know if they give you the matrix form or what form. Do they give you matrix?
No, not for cylindrical.
Or determine, what do they do? Just tell me what they have.
You've got 1 over rho, dAz over dV.
D,
AZ.
all right, so it'd be DHZ, dphi, right? Because we're using H, not Z. A. Go ahead.
Minus dA over dZ.
Minus what?
dA over
DH over what? DZ?
Yes.
And this is in the A rho direction? Correct. A rho? Okay. Keep going.
Then plus, in brackets, dA rho for dH rho over dZ.
H rho dz minus DHZ d rho.
Yes.
DH rho, or I'm sorry, D rho, correct?
In the AP direction.
A phi. Go ahead.
1 over rho open bracket. D rho AP or H
D H phi D. Go ahead.
rho. And there's an extra rho on top of that fraction.
Here.
Of the fraction you just wrote, it's D rho AP or D rho HP.
Inside the operation.
Yes.
Rho H phi.
Yes.
Okay. Go ahead. Minus.
dH rho over d phi in the AC direction.
Alright. Alright, so that's the operation we do. I'm just going to go through. We're going to talk about this. This is a straightforward kind of deal. You just set it up and then evaluate it based on the definitions of the derivatives. Y'all follow me? Go ahead and do it with me. So if we do this, first one, let's do this first of all. What is HZ? It's this, right? That's HZ. Y'all follow me? Coefficient of Z, AZ. Believe it or not, some people will miss this. They don't understand it. Everybody clear on that? That's what HZ is. It's the coefficient of AZ. This is what? It's H rho. Do y'all follow me on this? It's just the coefficient of the unit vector would be the H sub rho, H sub Z, or H sub phi if there was one. Are we all clear in this class? Now, next thing is you'll notice that H phi is 0, right? Y'all agree with that? All right, so anywhere there's an H phi, you get rid of that derivative, first thing. I'm just showing you how I would go about simplifying. Y'all follow me, class? It's methodical. So get rid of this. Here's an H phi, right? Get rid of that. Now we're down, we've got rid of some stuff. Next, when we look at this, go ahead and evaluate what's left. For this one, we have 1 over rho dhz d phi. This is hz, right? Derivative of that with that respect to phi is derivative of 1 over cosine. 1 over cosine is what? Secant, isn't it, class? So it's a derivative of secant. I think the secant function is the weird one. It's like natural log of cotan or something. I forgot the actual value of that. But I'm just going to go through this. So I'm taking the derivative of this, and I'll put this in here so we can talk about it. So we have minus rho squared, and then we have the derivative with respect to phi of 1 over cosine of phi here, and it's a rho. Plus, when we look at this, they have a derivative of h phi with respect to z right there. So of h rho, right, with respect to z. And that's going to be simply 1 over sine theta, or sine phi, pardon me, minus derivative of hz with respect to rho. Take a look at this. Derivative of this with respect to rho is just going to be minus 2 rho over cosine phi. Do you all agree with that, class? Let me see this right. So this is going to be minus a minus or plus 2 rho over cosine of phi in the a phi direction plus, and then we have dh rho d phi, and so then we have 1 over z. We actually have 1 over rho here, and then we have, it's minus, derivative of that with respect to phi is minus the z times derivative of this with respect to phi, and let me put that in there. So it's derivative of sine theta with respect to phi. 1 over sine theta, pardon. So that's the operation we need to do. Y'all with me, class? Is this what you did, by the way, when you did? Who asked me this one? You did? Is that what you did?
I don't know.
Well, how many tried this one? Now, the only thing you're doing, the only thing you're doing is just methodically going through and evaluating the definition of a curl. That's it. It's tedious sometimes. This one's one of the worst ones, in my opinion. So if you look at this, we've got this one done, right, class? The a phi one's done. Here, this one, we have to evaluate 1 over cosine phi. What's that going to be? You can do, you can do it a couple ways. I don't know how Wimmerspoke does it, but if you take the derivative, right, with respect to phi of cosine of phi to the minus 1. That's exactly what you're doing. Do you agree with this, class? It's 1 over cosine. It's cosine of minus 1. You take a derivative of that, what do you get? Minus 1, right? And then you take what? The derivative, and then you have to take this over what? Cosine squared of phi, right? This is like derivative of u to the minus 1, right? So it would be minus 1 over u squared. Do y'all follow me on this? And then you take the derivative of this. What is it? Derivative of cosine is? Minus sine. Isn't it, class? So this gets rid of the minus, so it's sine of phi. Now, I'll tell you, this right here, I mean, you can probably look up this thing, but I see a sine over a cosine, I think tangent, right? Tangent theta over cosine theta. Do y'all agree with that? I mean, it doesn't matter the form. This is one form. So I'll just leave it as sine theta over cosine theta for that part. And that's this one. So I have sine phi over cosine phi, hopefully squared. I don't know what this book is. All right, what about this one? What's the derivative of 1 over sine? And you can, I don't care, you can look this up directly because 1 over sine is what, cosecant, right? You could just look this up if you want. But I have derivative with respect to phi of sine phi to the minus 1. Does everybody follow me what I'm doing here? I mean, make sure, hands up if you do. Y'all with me? I'm just defining the definition of the derivative. If you don't know the derivative of a cosecant, and I don't remember that one off the top of my head, you can do it this way. So you get minus 1, that's 1 over the sine squared of phi. Then the derivative of sine is cosine of phi, right? And so over here, let's do that. So this, I'm going to get rid of this. There's a minus sign. I can get rid of that. So I still have z here, and then I have cosine phi over sine squared. And again, this could be what? A cotan over sine phi. So you can do it any way you want, but this is the form. Everybody follow me on this? All right, now he evaluates this function at these points. This is one of those tedious ones. I don't know why I put this in here. But if you evaluate it at rho equal 3, well, all right, I'm going to just say, hold on. Did I forget a minus sign there? No, I didn't. All right, so this rho goes away, right? And then they say rho is equal to 3. Where else? 3. I'm just putting it in here, class. And 3. And then he has what? He says phi is 60 degrees, okay? We'll do the 60 degrees. So if I have this, cosine is 60, isn't that 1/2, class? Cosine is 60, 1/2, how many agree? All right, you square that, you get 1/4, up top is 4. You all agree? That's 4 times 3 is 12. And then sine is 60, isn't that square root of 3 over 2, class? I'm just leaving it like that for now. We just talked about sine of 60 is square root of 3 over 2, right? So in this case, it's going to be 2 over square root of 3. What is the pain? Now what about this one? Cosine of 60 is 1/2, correct, class? So it's 1/2 over 6, or that's 12. Unless I did something wrong. And this one, what do we get? Z is, let me see, 4, right? Boy, this is crazy. So this is 4/3. And we have cosine, right, of 60 is 1/2. Just going to put it in. The sine of 60 is square root of 3 over 2. If you square that, you get 3 over 4, right? So It's 1/2 times 4/3. And I don't know his answer, but can you tell me what this number is? Just tell me if we got one of them right. I think we did. But so that's minus 6 times square root of 3. Boy, I don't know that. Say again?
You said 10, negative 10 a row.
All right, so what's minus, so that's 6 times square root of 3, what is that? Tell me what this number is. Is it minus 10? I don't know.
It's negative 10.39.
Pardon? Minus, is that what you got when you calculated? Minus 10.39? Anybody else? Anybody else? I'll trust you on this one. What does he have? What did you say he has?
10.
Well, we're off by 0.39. I wonder if we rounded or if we messed up. I think I'm right with the way I did it, but I don't know.
Yeah, your second answer is right.
What's that?
Like it's the same, I guess, that he has, other than the final answer.
Did he put, well, then he could have just omitted this, but that's the form. You're asking about this. This is how you go about doing it. Now, the only real point about this, we're spending a lot of time on the details of the curl evaluation. But when you're evaluating a curl, think about it this way. You're just being a good bookkeeper. There's a lot of little details you sometimes think, oh, I hate to do it. You have to force yourself to be focused and get the last thing done right, or else you're going to pay for it in the final answer, and that means you're going to lose a lot of points. And in the real world, what happens, you can lose, your company can lose millions of dollars if you mess up things like that. You have to learn to be focused. And anything that's serious, I calculate at least twice. I'm very, very paranoid about making mistakes. And it's easy to be casual and make mistakes. I'm just warning you about this. Okay, I'm going to say, is this part right at least? When we take 2 over square root of 3 plus 12. Let's see if we get that one right. I don't know. Hoping we do. Can anybody do that for me, please?
Yeah, it's like 13.15. I think you just rounded.
All right, this is 13.15 feet. And what does he have?
13.
All right. Look, I didn't do it. You can yell at him. I saw him. He's upstairs. Just go up and say, I think you'll feel paranoid. Is the last one right? I'm almost afraid to ask. Well, look, we got what? We got 4 over 2. That's 2. 2 times 4 is 8. Is it 8/9? Can it just take, isn't that right? Is that his answer? Can anybody, is that his real
Yeah,
answer?
it is.
It's just,
Yes,
it
it
has
is.
it in decimal form, but yes.
Yes, fine. All right, but that's how you do it. Now, I'll warn you about one thing. If you don't feel comfortable with some of the derivatives, just look in a table. Because sometimes, if it's like 1 over secant squared phi, all right, I would never do that one. I would take secant and make it cosine up top. You know what I'm saying? I put them in terms of things I remember. The cosine, really cosine, cotan, and cosine. I don't remember the derivatives of the definite, but I know it's just 1 over the other trig function, so I do the derivative of that. That's all. Okay. Any other questions? It's not a bad. You picked one that's kind of a pain. And I would give you the curl of that. The way, this is not the way I think I remember curl. A lot of this I do with determinants, but he has the matrix form of the derivative, I think, for Cartesian in your book, doesn't he? And when he does the curl, he has like the determinant form. Isn't that right? All right. To me, that's the way I remember most of these. I don't remember them, the expansion form that we showed. All right. Another question? That's a good question. I want to do some of the self-inductance, mutual inductance problems, and then also want to talk about magnetic circuits today before we jump into boundary conditions and a few other things. Y'all with me? How many tried some of these problems with magnetic circuits? any problem that you would like me to do with magnetic circuits? Because I'll pick one, but I'm just asking.
354.
3,
54.
454. All right, let me see. What is that, this one? Can you tell me?
Yep. Okay. There's like two wires,
Parallel.
parallel wires.
All right. So you got an infinite wire, you got a current I, we're going to assume another infinite wire. Do they have a radius or not? They have to. Don't they both have a radius?
Radius A. Radius A.
All right, so they have a radius of A. And this one, this is a classic problem. You probably remember it in physics. Parallel. Or we don't even have to assume. We're going to assume that it's differential. So I here, it's probably like a transmission line. Current in one side is the opposite current in the other. Y'all follow me, class? I think this is the problem. Is that right? And what does he want? The self-inductance per meter?
He wants the inductance per unit. Find the inductance.
This is self-inductance. All right. Now this is an interesting problem. Doesn't he say something about a transmission line or current? In one direction is the opposite in the other, something like that. If he doesn't, here's what he's really saying. Think of an extension cord. Y'all know what that is, right? Current in one side of the extension cord is equal and opposite to current in the other as it flows. Y'all follow? This is the problem we're dealing with. Now, when we talk about the inductance of this system per meter, what we're really doing is this. We're saying, what is the separation distance center to center?
D. Oh wait, no. Distance apart is D, and then like D minus A is the separation.
Center to center is D.
What is
Center to center is D, and then the same is difference from the outsides, like the inside.
It would be minus 2A. It would be D minus 2A because they have a radius of A, right?
No, so it's D.
He's shaking his head. I better take a look. These are the kind of problems. If you told me the radius is A and center to center is D, that means
Oh, he does from 0. He's saying that He's saying that the left one is on 0, centered like on the z-axis.
but is this at 0 right here?
Yeah.
And this is at
So the
D.
right one's D minus A. With the
yeah, but that's all right. It doesn't matter. You know, as long as you know center to center and you know the radius, assuming the radius is in both, that's all you need. You ready, class? Now, there's an internal inductance that we'll talk about. I think did I do the internal inductance in wire? I thought I did. How many remember me doing it? And this is always troubling. I'll go through that again. Here's what they want though. They wanted the inductance outside the internal part of the wire. What they want is the inductance associated with magnetic energy that would flow here. Now this is a really good problem and it's important to appreciate this. So here's what we're going to do. We're going to find the magnetic flux from this current in this region. This is only going to have a height of 1 meter. And we know the center to center separation distance is going to be simply, what? D, right? As he said. So first of all, if you have a current, just an infinite current, you can call it on the z-axis. And you're a distance rho away, you've got to know this one. What is the value of the H field going into the board? Remember, use the right-hand rule. Following the direction the current flows, your fingers show the direction of the H field. Do you remember what it is? Normally, we've got it from Ampere's law. If we go around the path, the integral of H dot dl, which would be 2 pi rho H, is equal to the current penetrating that loop, which is I. So the H field itself here would be what? I over 2 pi rho. It would be in the A phi direction, or it would be into the board. Y'all follow me? Now, if we multiply that by mu naught, we have the B field. Do you agree with that? Try to be really clear about this. This is not a hard problem. So if we want B, that's simply equal to mu 0 times H, and that's going to be mu 0 I over 2 pi rho A phi. Now we have the B field. We've got the B field from this wire if we assume the current on the axis. Y'all follow me? How many understand what I'm saying so far? With me? He's looking on his phone or his tablet. All right, that's the B field anywhere here. Now we need the magnetic flux caused by this wire. I'm going to tell you one thing right now. Here's where the trick is. You'll notice if you look at this, that if we calculate the B field from this one, just listen to me, and then we integrate the B field dot ds over that surface, we're going to get a value. Do you agree with that? I can make the argument it will be identical to the value we get as if now we calculated the B field from this one, it would be going into the board integrated over that region. How many agree with that? All right. It will be the same in magnitude. And it's additive, which means if we calculate the total flux just from this current right here and multiply by 2, we would have the total flux penetrating this surface. How many agree with that? Y'all with me? I'm telling you a simple way to do it. So what I'm going to do is this. I know that's the B field. So now I'm going to go ahead and say the total amount of magnetic flux penetrating here is going to be equal to 2 times the integral, and it's a double integral, of the B field I just calculated, which is going to be mu 0 I over 2 pi rho A phi. And then I have to dot it with a differential surface. Now, I'm intentionally using cylindrical coordinates. So if this is the rho axis in that direction, phi would be into the board, and this would be the z-axis. You all follow me on this? Y'all with me? So that means the differential surface would be what? It has to be d rho dz in the a phi direction. You all follow me? Have to have a differential radially, would be d rho. Vertically would be dz, and it has to have a direction perpendicular to both differentials or a phi. How many see this right? You good with that, Jonathan? Or you with me on that or not? All right. Now, what about the limits of integration? This is another thing. We'll get to the dot product in a second. The limits for rho go from where to where? Be careful about this one. It doesn't go from 0. Where does it start? At A. Y'all follow me? It starts at the radius. We're external. We're not inside the wire. So from A to what? Class? D minus A. Because he centered the first wire on the origin. It's Z equals 0. Do y'all follow me? I mean, rho equals 0. Do y'all follow me? What about the height integration? Remember, it's per meter. H is from 0 to 1. That integration I usually ignore, but I'm going to do it. Now, what is that going to be? That means the magnetic flux is going to be 2 mu 0 over 2 pi. You can take all the constants out in front. Might as well take I out in front. Right? Now I got A phi dot A phi, which is 1, right? So that goes away. Now, when you do the d rho integral, you have the integral of 1 over rho d rho, which is natural log. It's hard getting a response. Natural log. Y'all follow me? This is not hard to see. So natural log of rho, it's evaluated from, we'll get to this, from A to D minus A. And when we integrate dz, we get Z. Evaluated from 0 to H is H. And since H is 1, I'm going to ignore it. Y'all agree? He wants it per meter. Now, if we have this, what does this come out to? The 2's cancels. I have mu 0 over 2 pi, right? I. And then we have the natural log of D minus A over A. A lot of times they assume D is much, much greater than A. If they do that, they just have natural log of D over A. Y'all follow me? How many see this right here? Did you have a question?
Would it not just be over pi since the 2's cancel out?
Yes, it would be. That's because I wasn't very attentive. Y'all with me? You're right about that. Thank you. Y'all follow me on this class? All right, now, that's the flux. How do you get inductance from flux? Anyway. What did we do? We started assuming an I. We divided by I now to get inductance. Inductance is never a function of I. When we divide this by I to get the inductance, and this would be per meter, right? The self-inductance per meter, that's going to be simply what? Mu 0 over pi times natural log. Does he assume D is much greater than A or not?
Yes.
Then just put D over A. And this would be henries per meter. Now, mu 0 is 4 pi times 10 to the minus 7th, right? Since you got a mu 0 there by pi, that's simply 4 times 10 to the minus 7th. Natural log, we can do it this way. I don't know what the form is he has, but 4 times 10 to the minus 7th, and it would be natural log of D over A, and this would be henries per meter. Is that his answer? Anybody? Who asked me about this, by the way? Who suggested it? Did you? Is that his answer? Anybody confirm? I'm sure it is. What?
He's got a
What?
Yeah, what happened to D minus A after you divided by I?
We assumed D was much greater than A, right? So D is much greater than A, D minus A is D.
Okay.
That's the only thing. I mean, I'm saying if they said that, that's the assumption. Does he have D minus A in his answer?
Yeah, he has U not
All right.
pi times 1/4 plus.
If he has D minus A over A, that's fine. Does he have that?
Yeah, but he got 1/4
For what?
plus natural log of D minus A.
So does he give you a value for A and D?
No, in fact, again, you said each wire can be solved using the energy approach, and he does like an L over H.
Wait a second. Does he have 4 times 10 to the minus 7 to the front?
No, he just uses mu.
He has this natural log as 1/4?
No.
What are you saying with the 1/4?
Someone say it in one coherent answer.
Okay, he has his U naught over pi
That's correct.
multiplied by 1/4 plus the natural log of D minus A over A.
1/4 out in front of the log?
Added by the log, yes.
Oh, he's talking about the energy internal to the wire too. All right, I didn't get that. This is the inductance that has to do with the external inductance. Now, if we are internal to the wire, I might as well do this part. We'll do it with the energy approach. So this is the inductance associated with the energy outside. All right, y'all with me? Now, let's go to the wire itself. For some reason, I thought I did this one, but I guess I didn't do it. Suppose we have a wire. We're just talking about the internal inductance of the wire per meter. This is called the internal inductance. And it's the DC internal inductance. We have a wire of radius A here, and we're doing it per unit length, L. Here are H. H is 1. Now, you already got that inductance, so I'm going to erase this. I'm going to tell you this is kind of an interesting problem. It's not that big of a deal, but it causes people a little irritation. So there's 2 ways to calculate the internal inductance per meter. We can use the energy approach. And remember, inductance is what? 1/2 Li squared is equal to what? The magnetic energy in a region of space. Y'all follow me on that, class? How many remember that 1/2 Li squared is the energy in an inductor? That's the stored energy that's available. Now, if you take a look at this, all right, if we use this energy approach, here's what we need. We need to first, we assume I, and from I we get J. Y'all hear me on that? Now from J, we're going to go ahead and get H. From H, we get B, or we don't even need B in this case. And from H, we get the magnetic energy density. Write this down. I think I put this down one time. but I don't remember what lecture it was. This is the magnetic energy density. Let me just talk about this right now because this is going to be important. Boy. And I'm going to get rid of this right here. All right. After we have the magnetic energy density, which by definition is 1/2 mu magnitude of h squared, and this would be in joules per meter cubed. After that, we find the total magnetic energy, and that's simply the integral of magnetic energy density over the volume we're talking about, and from there, comes back to here, stick that in there. We assumed I, we calculate L by just saying L is going to be equal to 2 magnetic energy divided by I squared. This is the actual way you do it, the energy method. Everybody with me? Did you have a question? You looking real?
What's inside of the integral?
Huh? Oh, this is the magnetic energy density over the volume. I'll try to be a little neater. This is equal to an integral of this of 1/2 mu magnitude of h squared over the volume considered, whatever the volume is. That's all it is. But we'll do this problem. And this is going to be the magnetic energy in a wire for a unit length. You have to divide it by the current squared causing that energy. And that would be the inductance for a wire of length, internal inductance of length 1 meter. Now, if there are 2 wires, then what do you have to do? Multiply by 2 because you have current going this way and current going this way, right? For this problem. So, for this problem, let's go ahead and do this. I think you'll get it. We're going to assume I might as well call this the z direction, doesn't matter. All right, so we're assuming I. Now the next thing I want, we're assuming I is uniformly distributed over the cross section here. Now I want J. What's J going to be anyway? Yeah, it's going to be the current divided by the cross-sectional area. So it's going to be simply what? I'm going to say J would be equal to I over pi a squared in the AZ direction. That would be amps per meter squared. Y'all follow me? Current by area is the density, it's J. You're all with me. Now from that, I need the magnetic field. This is kind of a classic problem. So now I have to say, well, it's internal. If I want the magnetic field, and I hope you can understand this, if I take something of radius rho, and I draw a circle there, I'm trying to show you in the cross section, but it's hard for me to get perspective. And I want the total current penetrating that loop, and that would be the integral of h dot dl. Do you all follow me? How many understand that concept? This is something you had at St. Pierre's Law. It's very important. So from there, I get h by saying the integral of h dot dl around a closed loop is the I enclosed, right? Well, the integral of h dot dl at a radius rho is just 2 pi rho times the h. Everybody with me on that? In the back, can you all follow me? So this is going to be 2 pi rho hv. It'll always be this form, always. Now on this side, how much current is penetrating that? Remember, this current density J is a constant, right? So if we take the current density, amps per meter squared, and we simply multiply it by the area of that loop, cross-sectional area of a loop rho, we would get the current. How many see that? Y'all with me? Do you all see it? All right. So that means this is what? Actually, this is part of the problem we did one time. I think we did this whole problem. So this is going to be what? Pi, right? Times rho squared, right? That's the area times the current density J. And J is this. So it's going to be times I over pi a squared. And you can go ahead and take a look at this, but what happens is I have I, that's on this side, and it's going to be times quantity rho over a squared, and that's equal to 2 pi rho hv, or if I want hv, I take divided by 2 pi rho. Now, I'm gonna go ahead but you all follow the technique. It's nothing tricky here. I'm just doing the substitution. I come down here and I can say, therefore, my h phi is gonna be equal to, when I do this, it's gonna be 2 pi I, right there, and then it's gonna be rho over a squared. And that would be in the a phi direction, and that would be amps per meter if you want the units, but that's h phi. Does everybody follow me how I got that? I want to be sure about this. Y'all good with that in the back class? Now, next I need the magnetic energy density. I need to evaluate this energy. So let me do that here. The magnetic energy density is going to be 1/2 mu 0 times h squared, magnitude of h squared actually. So that's going to be 1/2 mu 0. If you square this, what do you get? You get 2 pi I divided by a squared squared. And then you're going to have rho squared. Can everybody follow me? I'm just going through the format. Yep, how many see this right? That's the energy density. You'll notice it's proportional to rho squared. There's h phi. Now, I'm going to come back over here, and I've got to integrate to find the total energy per meter. So now, that's the density. Now to find the total energy, it would be a triple integral technically, so I'll put it down as a triple. And it would be the magnetic energy density, which is 1/2 mu 0. And then it's going to be times 2 pi I over a squared. You can see we can simplify this somewhat, times rho squared. Now what's the differential volume in cylindrical coordinates, class? Differential volume. Well, there would be what? It would be d rho times what? Rho d phi, that's the wiper arm length, times dz. Do you all agree with this? All right, now we put the limits in. D rho goes from where to where? From 0 to a, right? This is inside the wire. When we talk about phi, it goes from 0 to 2 pi, exactly right. 0 to 2 pi. And then z is from 0 to 1. H will be 1. This is per meter. So 0 to 1. And that is h. All right, now do it. So we get omega m. Let's take a look at this. Let's take all the constants out in front. So I have 1/2 mu 0. I have 2 pi I over a squared, whole thing squared, right? Then I have, I think that's it. I integrate rho squared d rho. I get rho cubed. Wait a second, did we miss a rho? No, rho cubed. See, there's a rho here, rho here. Rho cubed d rho is rho to the 4th over 4. Evaluated from 0 to a is going to be a to the 4th over 4. It's good to do this one time. Do you all follow me on? How many see what I'm doing here? Can you all understand it? All right? That's the first part. That's the d rho integration, because there's a rho and there's a rho squared. Then I integrate d phi. There's nothing in here that depends on a phi. So I get phi from 0 to 2 pi is just 2 pi. And then I integrate dz from 0 to 1. I get 1. So that is the magnetic energy total magnetic energy. Y'all follow me? How many see this? Now I want the inductance. This is a beautiful thing. So I can say that's equal to 1/2 Li squared. You all agree with that? This would be the internal inductance. If that's the, does everybody follow me at this point? I'm trying to finish this up before class. Y'all with me? All right, now we solve for L. This would be the internal inductance. There's a very interesting result I need you to just appreciate with me. So if I go ahead, can you all see I can get rid of the 1/2 right off the bat? Everybody? So the 1/2 goes away. Next, you all see I can get rid of I squared. How many see that? It appears on both sides. Now, inductance will never be a function of I for linear materials. So I'm going to get rid of this, and I'm going to get rid of this. Now, what do you see happening here? I'm going to have a mu0 remaining, right? This was important. I'll have mu0. But what happens otherwise? Now take a good look at this. Just listen. I have that squared, right? That squared, that's a to the fourth, a to the fourth. A goes there. Y'all agree with that? All right, now we're going to get 4. So what is that going to be, class? Take a look at it. That's mu0 is, L is what? Let me see on that one. That's right. That's right. I think that's going to be the answer right there. Does he have this for the internal inductance of the wire per meter? This is for a single wire. I'm trying to finish this up here. I don't know where he has it, but he should have. Give me 1 second in the book. Hold on for 1 second, class. This is on page 269. It's equation 4.105. Take a look in your book, page 269, equation 4.105. That's the internal inductance per meter, internal. Y'all with me? Now, I'm just trying to finish this before we leave. We had the actual outer inductance as, just listen to me, it's mu0. We really have, at the end of the day, we had 10 to the minus 7th, right, times the natural log of d minus a over d. Y'all follow me? A. I'm trying to just write this down. That was what we had before, right? Now we have to add 2 of them. So when you do, you're going to have plus mu0 over 8 pi times 2, or mu0 over 4 pi. Y'all follow me? That should be his answer, is it? I'm trying to make sure I got it. I'm sorry I didn't get more time with that proof. Go through that proof yourself. And I may have messed up because I was trying to get it in. I was in a hurry. So on Friday, your quiz will be on inductance, both mutual and self. I didn't have a chance to do a mutual inductance one. Y'all with me? So make sure you do the problems. It's going to be related to that. I may ask you to do a curl, but if I do, I will give you the definition of the curls. You just have to know what the derivative of x is with respect to x and stuff like that. Y'all with me, class? All right. Thank you.